Today I present the work RST Discourse Parser for Russian, an experimental study of deep learning models. At first, I'll give you the outline of RST discourse representation in Russian corpus. Then we'll discuss the deep learning models for discourse segmentation and the discourse tree construction strategy we used to build the first discourse parsing pipeline for Russian. The widely used discourse model of text is rhetorical structure theory, which represents the text as a constituency tree. This discourse model was chosen to build the first RST corpus for Russia, discourse corpus for Russia, among others, because it allows us to represent each text span from the document as a part of the larger constituency tree, and the other approaches do not allow us. The rhetorical structure theory was developed by Mann and Thompson. It represents the text as a constituency tree containing discourse or rhetorical relations between text segments, discourse units. These units can play different roles inside the relation. Nuclei contains more important information, while satellites give supplementary information. There are multi-nuclear relations. Some of them are not non-binary. In multi-nuclear relations, all discourse units are equally meaningful, and mononuclear binary relations are those where one of the spans is a satellite. In this example, you will see two mononuclear relations. Discourse units, the leaves of the tree are the minimal or elementary discourse units, and discourse units of different levels are combined with the same set of relation. In Russian RST corpora, we have more than 3,300 texts of various genres, news, blogs, and science, popular science. And for annotation was used RST web tool. Here you can see the annotation sample from the news subcorpora. The multi-nuclear relations joint comparison and contrast, and mononuclear relation elaboration. The discourse parsing pipeline consists of three models: the segmenter, the structure classifier, and the model for classification of discourse relations. The first is used for text segmentation, and we solve the problem of discourse segmentation as a sequence labeling problem. And for each token in the sentence, we try to predict one of two labels, begin or inside. And the begin label means that the current token is placed at the beginning of a new elementary discourse unit. Following the works of Wang and Müller, we trained BLSTM and BLSTM-CRF sequence labeling models on the contextual word embeddings and character level convolution filters. The results show that CRF sequence labeling improves the recall metric, and the language-specific Elmo model, we used Elmo model from Rus Victorious for Russian, slightly improves the segmentation in terms of F measure. For discourse tree construction, we adopt the greedy bottom-up algorithm presented in the Hilde parser for English. It employs a cascade of models for structure and label prediction. The structure classifier predicts if two units form a higher level unit, and the second one assigns to the higher level unit a relation and a nuclearity type. We also propose to use a confidence threshold for the granularity levels. We apply tree construction algorithm to each granularity level sequentially from a single sentence to the whole document, and to the discourse units do not merge if the score that is predicted by structure classification is less than the confidence threshold for the current granularity level. For the classification subtasks, we employ the BMPM multi-perspective symmetric matching model. It was originally proposed for the task of sentence matching. In the BMPM model, two text inputs. In our case, left and right discourse units are encoded in BLSTM encoder, and the encoded vectors are matched in both directions on each time step. The matching results are then processed by another BLSTM layer, and both outputs of the aggregation layer are concatenated into a matching vector used for final classification. As an input of the model, we used the contextual vectors obtained with Elman model. And in case of structure classification, the feed-forward classification layer also takes as an input an additional feature that indicates whether both text spans are located in the same sentence and whether they are located in the same paragraph. We compare the performance of three classification models. The baseline model is a feature-rich SVM model using various lexical, morphological, and semantic features. We improved this model with an accurate feature selection and additional features. We'll discuss them later. We also train a BMPM model, which we use additional features in terms of granularity features, indicating whether DUs are located in the same sentence/paragraph. And we ensemble two models to achieve the best result, which is presented in the table. We can see that the baseline feature-rich model outperforms the neural BMPM model on the test set, and the ensembling technique allows us to achieve the best result for the structure classification. The aim of relation classification is to predict the discourse relation or rhetorical relation with nuclearity type attached. Here we compare the performance of four models. The baseline model is the same. Is the ensemble of a cat-boost model with selected features and the linear SVM on the same handcrafted feature-rich set using various lexical, quantitative, morphological, and semantic features. We improved this method with an accurate feature selection and additional features. namely sentiment score and granularity features. In PMPM model for relation classification, we use as features only Elmo embeddings of true discourse units, and we apply the ensembling technique for the improved baseline model and PMPM model. These pictures give you an outline of classes in the Russian data set. There are 22 most frequent classes which were used for train and evaluation. And as you can see, the best performance was achieved on the classes that are hard to confuse with the other classes, which are attribution and purpose, although they are not the most represented classes in the dataset. Now, this table contains the scores on each metric for parsing on manually annotated discourse segmentation. There are detailed micro-average scores computed globally over the predicted and manually annotated spans from all documents, as well as macro-average scores computed as an average across the documents in the corpus. Metrics are given in terms of the standard parseval to its relation between binarized, manually annotated, and predicted trees. The span states for unlabeled tree construction, nuclearity states for unlabeled tree construction with nuclearities. Relation is for unlabeled tree construction with relations and without nuclearities, and the false score is in the last row. In our work, we developed and evaluated the RST Discourse Parser of Russian texts, including 3 components, namely discourse segmentation model, unlabeled tree constructor, and relation and nuclearity type classifier. We improved state-of-the-art results in discourse segmentation and RST relation classification for Russian with the help of contextualized word representations and PMPM neural architecture. We proposed the greedy algorithm and structure classification model for unlabeled discourse reconstruction, and we published the source code of the experiments along with the source code of the final discourse parsing pipeline. Thank you for your attention.
Thanks, Elena. Any questions concerning this work? I actually have 2 questions for you. The first is very practical, and the second is more generic. So first of all, which LMO model did you use? Have you trained it yourself, or was it pre-trained?
No, we used the pre-trained models from the Victoria's project.
Which one?
Sorry?
I mean, which one? On which corpus was it pre-trained?
On the news corpus.
All right. Yeah, and the second question is, how do you see what can be the practical downstream tasks for which your RST discourse parser can be used? I mean, in which applications can you find potential interested users?
Well, discourse parsing is useful everywhere where you analyze texts larger than one sentence. There are text summarization, machine translation, information retrieval, and so on.
Okay, thanks. And yeah, we're still slightly ahead of time, so we still have time for questions. Please feel free to ask. Simply unmute your mic and yeah. You can also do it in the chat if you feel more inclined to ask your questions in writing, then please just send the message to the chat. Okay, thanks, Elena. Then if we have no further questions, we can move on to the next talk.